ESF is the oldest, largest, and most distinguished institution in the United States that is focused on the study of natural resources and the environment. Hello and welcome to this edition of Improve Your World with SUNY-ESF. I'm Dave White. Welcome to the Gateway Center on the ESF campus. The final touches of the construction work are underway to complete an extraordinary building. Groundbreaking in 2010 was on a sunny but windy day. And here's a taste of what's been happening ever since. Now let's take a closer look at the design and construction of this building. It's a very, very energy efficient building.
And that is achieved through a combination of how the building envelope, as we call it, the walls, the foundation, and the roof are heavily insulated and also protected from unwanted solar gain, but capturing a lot of daylight in desirable ways, and the very energy efficient systems. The length of this building faces due west. It's got a fabulous view, but it's really unfortunate for solar gain. In other words, it's hotter, glarier sun than we want in the building. So we cured that by creating walls that are serrated. We call them flipper walls. They're not movable, but they look as though they might have flapped into their form. And the virtue of that wall is it makes the building entirely south-facing, where we can shade that with an overhang and allow daylight to come in the winter, but to be fully cut off from coming in at all in the summer. So we get desirable solar gain in winter to help heat the building, renewably, passively, no machinery necessary, but we get the advantage of self-shading in the sun, in the summer. Below the tile, the finished floor that we saw going in today is a concrete slab, and that concrete slab has a massive amount of plastic tubing in it, and that tubing is carrying a radiant circulating system to use the mass of the building to deliver the heat and to hold the heat. It's a more energy efficient system than heating by air, which is common in contemporary construction. We're standing on the ESF Gateway Building's green roof. We're right above the concourse where we were a moment ago, and we're looking at a 270-degree sweeping view, which is very unusual for an urban campus. So we really wanted to design the green roof to be a very special place in the building. Significant insulation under the green roof and the planting medium and the plants themselves help insulate it, lowering the energy load which has to be supplied by renewable energy. It also provides the occasion for lots of native planting for teaching and research, which is an integral part of the ESF curriculum.
That research actually started on the roof of the building next door to find just the right plants. This is what many roof gardens look like, doing the job of insulating the building to reduce energy usage, but the minimal substrate depth, generally less than 6 inches, limits the type of plants that can be used and can lead to a lack of variety in the planting design. The substrate for the roof garden being constructed on the Gateway building will range from 6 to 18 inches, and that opens the door for some innovative use of native New York plant species.
Well, the plant species are from two very rare natural communities in New York State that are north of here, the Alvars, northwest of Watertown, and along eastern Lake Ontario is another very rare natural community. So we picked the most drought-tolerant species that we could find from those really drought-prone natural communities.
The selected plants were set up in test plots on this roof for 2 years to see which thrived the best.
So these plants have been growing on Illick roof for 2 years. Pretty different conditions. Heavy snow 1 year, no snow this past year, extreme cold sometimes, extreme drought. They've been through pretty much the usual things that you might expect over 2 or 3 years. And we've lost only a few species. We actually have been surprised by how well some of the species have done.
Here's one that has obviously done well. The dune willow is a tall growing plant, something you don't often see in roof gardens.
From an ecological standpoint and from a structure standpoint, in terms of how you design a garden, how you design a garden space on a roof garden, you want to have some variability in height and things like that. So we're getting a larger plant which can tolerate the difficult growing conditions.
Some 50 plant varieties are being used, so it will be a dynamic landscape with something happening pretty much year-round.
It's a novel application, it'll be a novel design, and the fact that people can come out and engage it and look at it and experience it directly is good. One of the important aspects of that, I think, will be that the design community will have a new palette of plants that really increase the options that they design with when they work with green roofs.
This green roof will be three times the size of other green roofs we've designed, and perhaps the largest green roof in New England and in the Northeast United States. It's also very significant in the quality of the plants. These are not traditional green roof plants. They're special cultivars that are native to this part of New York State and will be very important in carrying out ESF's research mission. You can see behind me are those roof monitors we were talking about, which are integrated with the structure below. And they're emitting nicely controlled south-facing daylight and east-facing daylight. You also see smaller flipper walls, which are the same theme as the larger ones down below. They're actually blocking any solar heat gain from the west and allowing it from the south through windows that you can see are nice and operable into all the offices along this floor.
Here's what those roof monitor windows look like from inside the concourse of the building.
There's only one other thing, and that is deep daylighting. Buildings are good. Buildings are good in terms of their daylight if the light is very even. And as the concourse gets bigger here, we introduce what we call roof monitors. They're not skylights because the glass is actually in the vertical plane. So it's very easy to control the shading. And these are south and east facing. So the light here is beautiful, and it spills deep into the space and gives you a feeling of being a little bit in the outdoors, even when the space is quite deep. So that augments the light. The point of all this good daylighting is to have these fluorescent tubes not be on so much. So there'll be a good lighting level here in the evening, but not a reliance on artificial lighting more than necessary during the day. So, and you've noticed this already, all these lights work with the structure, everything works with the structure. So it's really a celebration of structure first and foremost, and then everything is integrated within it.
what you're looking at, basically both of them are environmentally harmful and neither of them are necessary. We've listed a number of different kind of characteristics, ways of measuring the difference between paper and plastic use in terms of impact on the environment. If you look at the amount of energy in consumption, plastic tends to be better, it uses less energy. If you look at the amount of energy used in transport, plastic tends to be better. The amount of space in a landfill that's used up, again, plastic tends to be better. The amount of water used, plastic tends to be better. If you look at litter and how long it stays around, you see plastic bags everywhere. Clearly, paper is a better option. If you're looking to the threat to marine life, paper is number one. Plastic bags tend to clog drains, which becomes a problem. In terms of the toxic chemicals in the bag itself, not necessarily in the production of it, they're about equal because of the way that the paper bag is produced. And in terms of recyclability, neither of them are terribly easily to recycle. You don't need to buy a specialist bag that somebody produced and is selling. They're good, they're better, the fact that you can keep using them. But I just tend to bring a couple of plastic bags with me and just reuse them.
The Gateway Center also houses a very innovative combined heat and power plant, a power plant that will supply the needs of not only the Gateway building, but the heat and power needs for other nearby campus buildings.
On the lower level of the Gateway building, we're now directly below the lobby, is the combined heat and power plant. So this is the mini power plant within the building. And architecturally, it posed three very important challenges. Number one, fuel storage. The renewable fuel here is primarily waste wood pellets. So we effectively had to create a silo or a bunker within the building. And we did it within the northeast corner, integrated with the facade. You can't probably notice it, but integrated with the curtain wall is the rise of a two-story pellet hopper. And that feeds an auger, that feeds a gasifier, that feeds a boiler right over here to the left.
The two systems, one is a biomass-based wood pellets that we're going to use as the fuel, and that will produce high-pressure steam, about 125 psi steam. That steam will move through a back-pressure steam turbine. So it's a technology that takes high-pressure steam, spins a turbine. While it spins, that generates electricity, and what comes out is low-pressure steam. That low-pressure steam we use to heat our buildings. So unlike traditional electricity generation, we're going to generate the electricity we need and make use of the waste heat. Most central power plants waste all that excess heat. So we're going to take about 75% of the energy that we put in, and that will become useful energy for us either in the form of electricity or heat. Now the wood system, we have a gasification boiler, a gasifier, we have a gasifier that will take the wood pellets, heat them without much oxygen around, and that produces a gas. Then we add air to that gas and burn that to produce high pressure steam. So that's how we do that. That's more efficient than just burning the wood pellets directly, and so we have lower emissions from that. That system we could have installed and it would meet all the emission requirements that we have today. But we've added to it an electrostatic precipitator. You can think of that as a series of metal plates that have an electrical charge, and the small particles of emissions that would come out are attracted and attached to those plates. So we reduce the emissions further and go beyond what's required by code in our emissions. And then occasionally you just shake those plates, eliminate the charge, shake those plates, and we collect some ash off them. But it's a technology so that we get the emissions from our wood system to be the same or a very low emission like in natural gas. Now the wood system runs efficiently as sort of a base load. We want to run it at a pretty constant output all the time. So to that we've added a natural gas boiler. We actually have two of them, one for the summer and one for the winter. And so we can follow our heating needs as we go throughout the day in different months. So we use natural gas as our fuel to move up and down to follow our heating loads that we have in the buildings. So that's one main source of our systems.
Second challenge is we had to deal with some of the logistics of removing the waste ash, and the lift and the drum feeders that you're seeing here were part of that solution.
We do get about a barrel of ash, 55-gallon drum of ash every other day from this plant. So it's relatively efficient in that it's not producing much ash, but we have a bunch of forest land and we grow willow as part of our research projects here, and we have a need for that ash, which is like a liming agent, increases the pH, so we can use that ash on our land to help recycle the nutrients from the wood that we burn back in to grow more biomass as we're doing that.
Right next to me is a window overlooking the CHP plant so that students can gather and understand the workings within the CHP plant. There are 22 pieces of equipment. They are laid out on the plant floor. There's a mezzanine deep in the space here, and all of the equipment and the piping runs and the duct runs are color-coded so that you can understand graphically how the system works, even if you're not here with an instructor.
Then we have a second combined heat and power system. That's a set of microturbines. They take natural gas and spin a turbine which generates electricity, and they produce waste heat. We take that waste heat and turn it into low pressure steam that we use to heat our buildings. So altogether, these systems working together, about 20% of our electrical needs, about 2/3 of our heating needs from these systems working together. This is a challenge because although the equipment's pretty big, it's producing a significant heat and power load. It's small for this technology. So it's new technology and something a little different. It takes people that would be willing to take, a little bit of a chance. We hired great architects and engineers to help design the system. We have a reliable system, but you won't see this set of components in any other building yet. This is going to be, a research project where we can show people about this technology, help them learn about it, and then it will help people become comfortable to adopt the technology.
In an architect's view of it, it's remarkable in that it meets 60% of the campus's peak heating load and supplies about 20% of its annual power requirement. So it's a mighty little power plant that this is. And part of that is the microturbine technology. Part of it is the strategic sizing of the boiler relative to the needs. And all of this was very well discussed during the design process to create the fusion of an architectural and engineering solution for the campus.
The system actually is a great value. So it has environmental benefits, energy benefits, and economic benefits. The system cost about $3 million altogether. We actually received a grant from the New York State Energy Research and Development Authority, NYSERDA, for about $1 million. So we have $2 million of cost, and it's going to save us about $400,000 a year when we start, and we expect those savings to grow as the price of fuels, electricity, and natural gas go up. So about a 5-year simple payback period for ESF. When you look at society as a whole, it's about a 7.5-year payback period, so pretty significant economic returns. And then we're not exposed to volatile price swings in fossil fuels in the future. And so we have basically a power plant that's going to provide about 2/3 of our heating needs for campus and about 20% of the electrical needs. There's really two sets of systems. We designed it this way so we had several different technologies because we have energy in our curriculum. We want to teach about it and have students understand how this technology works. When we look at how these systems compare to purchased electricity and steam, we're going to reduce the amount of fossil fuels required by about 65,000 million BTUs, or 65 billion BTUs a year. So it's a big number. And we do it two ways. One is we are more efficient at generating electricity and steam than traditional technology because we're making use of that waste heat. And the second is we're substituting wood pellets for fossil fuels. So each of those, the efficiency and the substituting a renewable fuel, each of those are about half of the reduction in fossil fuel use. This helps us be more carbon friendly, reducing our carbon emissions, our CO2 emissions, so that we reduce our carbon footprint, and helps us, like I say, with technology that will allow us to teach and help students learn how we can reduce CO2 emissions.
One additional note on energy. Just like these other buildings on campus where arrays have been installed on the roofs of Walters Hall and Moon Library, or the side of Baker Laboratory, solar power will also be used to help generate electricity at the Gateway Center. But that alternative energy resource will be added later.
So we've put in the conduit and wiring to be ready for a photovoltaic array. We're actually looking at going out to bid to acquire that PV array. It was outside of the scope of the budget that we had. But we want to put 100 kilowatts of PV on the roof. That will allow us to generate about half the electricity of this building, so it's a significant portion of this building. We can get to that percentage because the electrical use in the building is quite low because all the energy savings technologies that we've used. And we're going to go out to bid in a little bit of an innovative structure where we try and lease the equipment. There's some significant tax benefits that we can't take advantage of because the college is a not-for-profit. We're hoping somebody else would own the equipment, lease it to us, and we might see lower lease payments because of the tax credits that are out there.
Arbutus Lake is a relatively productive lake, and we kind of believe that probably other sources of water going into the lake, other inlets, would be fairly close to this based upon what we've done in some chemical balances. We are using this stream to look at how changes in atmospheric deposition, changes in acid rain, changes in the climate, droughts, different changes in the winter, how this affects the stream's hydrology as well as the chemical responses. There are times, like after a period of drought, you have conditions in the watershed which actually produce acidity, so you can have pulses of acidity which are very deleterious to the biota that occur within the site under certain types of conditions. And we're also looking at the water going out of the lake, so we can also look at how the lake itself affects some of these processes. And we also can link this to some biological changes in the lake as well as biological changes within the stream and associated terrestrial system, the trees and the soils around the stream. The design of the Gateway Center, along with all of the environmental attributes, is supposed to highlight the mission of the college. So a lot of thought went into what's become the final product. Admissions and outreach offices will be located here, along with conference rooms, a snack bar, and the college store. So this will be the place that many visitors will receive their first impression of ESF.
I think it's very unique, but it's also reflective of a bioclimatic design where the site planning and the form making of the building are the first line of defense against a building using more energy than it needs to for its needs. And you've noticed this already, all these lights work with the structure, everything works with the structure. So it's really a celebration of structure first and foremost, and then everything is integrated within it. A very cool thing is these prismatic forms are like sculpture penetrating up through the green roof. So they're a major feature up above as well. As you wander on the boardwalk, you're among plants, but you're also among these 4 big roof monitors so that it's a recall of the space below. And it's another way of making the Gateway building holistic, where you're aware of the upper and lower levels wherever you are in the building. Right here from the lobby, you're seeing what will be the start of a lengthy display of the Theodore Roosevelt Wildlife Collection and a large graphic design here which will display ESF Today. It will feature news and events and showcase student research as well as faculty patents in an ever-changing constellation of poster-like displays. So right here in the lobby, you start to get the feeling of this incredible energy and vitality of what is ESF. And just beyond these displays start to be the entrance into the large conference facility, reception for which would be held here in the lobby. Another feature of these serrated walls is to emphasize the length of this building. It's a double-ended building that has these big wood canopies on either end. And one of the reasons we did that is to exaggerate the extension of the building next to the very bulky carrier dome, to make this the signature of ESF, basically stand up to the heft of the carrier dome, which is massive by comparison to this smaller scale. Just outside here, we have the major east-west pedestrian spine of the campus that's leading from your new Centennial Hall up to Bray, your administration headquarters. And by locking into the circulation pathway and also looking at ESF, but the building closes up and almost precludes the view towards the SU campus, it's a building that very much plays with its neighbors and helps establish a sense of community among these adjacent buildings. And we'd like to say that the Gateway building has to be so memorable that even after you visited, you can still hold the memory of that image in your mind. That's what makes it a signature building. That's what makes it an identity building for this campus.
Back in the early stages of construction, when the steel beams were being hoisted into place,
don't forget to sign the steel beam.
one beam was set aside on campus for students, staff, and faculty to sign and write messages.
One thing that ESF has been extremely fortunate to have is the support relative to being able to produce, create, design, and construct these wonderful capital projects.
Oh, this is great. I actually was able to be a part of the beam signing for the Center of Excellence too, which was awesome. So.
What we have today, as you can see, is, I'm told, one of the last steel structural beams that'll go into that building, and that hopefully will be there for many, many decades to come. And what we're asking you to do now is to be part of that, and many of you already have, by actually signing within the beam, signing your name, and being part of this building long after it's been built, and perhaps long after we're gone, but the legacy will be in this building in the form of our names and our signatures and our comments.
This is cool. I'm wondering if we're gonna be able to see it though when they put it up.
They're big on leaving their names in the prison cells and where they've been.
That's it for this edition of Improve Your World with SUNY-ESF. Thanks for joining us. We hope to see you again next time.